Hello everyone, welcome back to our channel. Today we are going to be diving into something which is much deeper compared to what we had in our last video. Something which is very significant, something will help you to get a good mastery of what the design of experiments is all about, the 7 core concepts of design of experiments. So if you've not yet watched the last video, I urge you to go back, just have a glance through the video so you understand why it is important for you to actually learn design of experiments. Without wasting so much time, let's jump straight into the content of today's video. The first core concept of the design of experiment is a factor. What is a factor? What are factors? Here we mean those variables that can influence the outcome of an experiment. And here there are two types of factors. We have the qualitative and quantitative. Quantitative can be assigned a numerical value, while qualitative cannot be assigned a numerical value. For example, we have machine type for someone who wants to determine how different machines can affect the quality of a product. Operator type, how different operators handling those machines can have an influence on the overall quality. Different packaging materials, how different packaging materials can affect the quality of a product. So in experimental design, it's always very important and it's always the first thing to do when you want to conduct your experiments. Because of all, you have to identify all the factors that can potentially influence the outcome of that experiment. Looking at the project you are working on at the moment, can you identify all the factors that will influence the outcome of that experiment or the outcome of that project? Just take a quick overview of what you're working on at the moment and see if you can identify all the factors that can influence that process. The second core concept of DOE is what we call the levels. Here, when we talk of levels, what do we mean? We simply mean those specific values that your factors will take during the experiment. If you are monitoring the temperature, you can decide to monitor at 10 degrees, 20 degrees, 30 degrees, 40 degrees. These are the levels of that experiment. These levels, just like in factors, can also be numeric and categorical. For example, categorical can be machine type, operator type, machine type A, machine type B, operator type A, operator type B. These are the levels of operator and the levels of the machines. In a two-level factorial design, like in a standard two-level factorial design, these levels are always uh, attributed the high and the low, where the low assumes a value of -1 and the high assumes a value of +1. So the difference between these two values is always the experimental range. The range of this experiment starts from -1 to +1. In real values, from 70 degrees to 90 degrees. And the midpoint between these two is always called the center point, and it assumes a value 0. Again, looking at the factors you initially identified that may affect the process you are working on at the moment, and you try to assign levels to those factors. Let's see what you got. The third concept of DOE is that of responses. And in simple terms, what are the responses? Responses are simply the measured outcomes those outcomes you care about in your experiment. The whys, these responses, they're always affected by the factors and the different levels. For example, you may want to measure the texture of a food product. You want to measure the color, the protein content, the moisture content, the yield to someone who wants to measure the extractability of a bioactive compound. You may want to measure the tensile strength of a material. These are the responses. Again, I would like you to look at the project you are working on at the moment and see if you can identify all the responses that you can measure in the project. Now let's talk of experimental runs. What is an experimental run? In very simple terms, an experimental run is a trial with a unique combination of factor levels. It is a unique trial you perform, a unique experiment you run using different combination of your factor levels. And these factor levels, they're always predetermined in an experiment. And the number of runs in an experiment is always determined by your experimental objective. One is determined by the experimental objective. For example, if you want to optimize a process, it may be different from you simply wanting to know how factors affect the responses. It also depends on the number of levels you assign each factor, as well as the type of experimental design you choose. All of these will determine the number of runs in an experiment. And in experimental design, it's always good to go with the experimental type so long as it will help you achieve your objective. The experimental type with the smallest, with the fewest number of runs. The fifth concept of DOE is that of the experimental domain. Here, when we say experimental domain, what do we mean? We simply mean the range of factor combinations studied. This is actually the space where you want to conduct your experiment. This is actually where you want to collect your data. This is actually where you think your optimal points can be. And this point is always designed by the range of the factor combinations. And looking at the concept of experimental domain, you are going to find two other terms, the region of operability and the region of experimentation. Look at this simple diagram for a process that is affected by two factors, factor x1 and factor x2. Let's call factor x1 as time and factor x2 as temperature. You can see that it is already in a two level factorial design with two levels at -1 and +1 for each of the factors. So these levels intersect at certain points. The outline of this intersection forms the region of experimentation. This is actually where you want to collect your data in this experiment. This is actually where you want to monitor your drying kinetics in this particular environment, because you are sure that at this factor combination, your sweet spot is around that boundary. You are sure that your sweet spot is around that region. You could have conducted the experiment outside of this region, but because of many other factors, or maybe from experience, you've noticed that the sweet spot can never be above this region. So you may decide to optimize the extraction or the dehydration kinetics based on this experimental region. So this is basically what the experimental domain helps us to do. It helps us to locate the sweet spot as fast as possible. And when we determine the experimental domain, it will help us to uh, identify and reduce the number of experiments that we should have, conducted had it been we're running the experiments in a very wide space. Now let's talk of the seed concept, which is also a very important aspect to know in experimental design, the concept of coded variables. When we say coded variables, we simply mean transforming natural units to dimensionless coded units. You simply want to transform natural units to the dimensionless form, to a form which has no units at all. And there is always a way to do it. There is an equation that you can always use to transform natural units to the dimensionless counterparts. For example, let's still consider these dry kinetics involving temperature, time. Why is it always important to transform natural values to their dimensionless units? Let's say the dry kinetics for moisture content, MC, is equals to uh, the effect of temperature plus the effect of time plus the effect of temperature times time plus the intercept, then plus the experimental error. Why is it always important to convert these natural values to dimensionless coded units? You can see here that moisture content is dependent on the effect of temperature plus time plus the product of or the interaction between temperature and time plus the intercept, then plus the experimental error. You can see mathematically this may not be so good because it is like you are adding degree C plus seconds, like you are adding 10 apples to 4 oranges, which mathematically may not sound right. So it's always good to convert coded values to dimensionless, uh, in fact, to convert natural values to dimensionless coded units. And you can always use equation 1 to do it. So in this equation, V stands for the actual value of factor X. Let's say factor X is temperature, the actual value of temperature. Then U is a center point. U is a center point. Du is the increment value from one experimental point to another, while x of I is the coded value of x. For example, you may be asked to, in an experiment, to convert from 50 degrees to coded values, convert 90 degrees to coded values, convert 0.5 concentration to coded values or 1% concentration to coded values. So in the standard form for a two-level factorial design, the coded values are always from -1 to +1 for a standard two-level factorial design. It's always from -1 to +1, where -1 is always the lower level of factor x, and +1 is always the upper value of factor x. Let's go further with the concept of these coded values because it's very important. And you will always be converting from coded values to real values and from real values to coded values. In fact, most of your responses, most of your optimal experiments will never be the same as the base factor combination. There will always be values in between those factor combination. And you cannot work with all factor combinations. The basic objective of experimental design and modeling is to help us predict other values which are in the experimental domain or the experimental range. And because of cost, we cannot always evaluate for those values. So the objective here is to predict some of those values. And when you predict those values, you always have to convert them back to their original form, or maybe if they are in their original form, you may have to convert them to coded values. So that is why it's very important to go further and learn how to convert real values to coded values. And here, let's look at a simple example. In a company, the management has tasked this chemical engineer to optimize the yield and purity of a chemical. And this chemical is affected by, the yield of this chemical is affected by some factors: the temperature, the amount of catalyst, and the reaction time. So the engineer from previous knowledge have already known that the best temperature or the temperature range of this chemical reaction is between 50 degrees and 90 degrees. The catalyst concentration is between 0.5 and 2.5, while the reaction time is between 2 and 6 hours. So the first thing to do is, first of all, look at the equation that has been uh, specially assigned or designed for converting real values to coded values. And like I said earlier, V is the real value, U is the center point, du is the increment, while x of I is the coded value. And like I said, in a full factorial or in a two-level factorial design, the levels are always between -1 and +1. And the distance between the two of them is always the center point. The center point in this case is U. So U is defined as the upper value plus lower value divided by 2. So U for temperature, x1, is 50 plus 90 divided by 2. So we are getting 70 as a value for U. Then du, if we make du here the subject of the formula, we are going to have uh, v minus u divided by x of I. Like I said, this v is the actual value, u is the center point, and x of I is the coded value. So this v can either be the lower limit of component x1 or the upper limit of component x1. So if you choose to go with the upper limit of component x1, also make sure you divide by the upper limit of the coded value. If you choose to go with 50 here, also make sure you divide by the lower limit of component x1. So at the end, if you have chosen 90, so it means we are going to divide by 1 such that the u or the increment be 20. So the temperature or the equation that is applicable to converting any value from 50 degrees to 90 degrees would be this equation. So you can convert any value from 50 degrees to 90 degrees to their coded values. If you do the same for x2, which is catalyst and time, we are going to have there are various equations where you can use to convert their real values to coded values. So looking at this equation or using this equation, can you convert the temperature, let's say 60 degrees, 70, 80 degrees for temperature, then 1%, 1.5%, and 2% for catalyst. Then for time, you convert for 3 hours, 4 hours, and 5 hours. Let's see what you got. And you post your answers in the comment section. Now let's look at the seventh concept of a design of experiment. And here we are looking at the pseudo variables. The pseudo variables here, they are synonymous to the coded values that are used in process design. But here we use them in mixture experiments where the sum of the component proportion is always equal to unity or 100%. And just like the coded values where we had an equation to convert real values to coded values, we also have a similar scenario here where here x of I with a small zero on it is a pseudo value. Capital X is the real value. L of I is the lower limit of component X, and L is the sum of all the lower limits of the component proportion. Again, let's go deeper into the concept of the pseudo values because it's very important, especially to those who are in the food, the pharmaceutical, the chemical, in fact, in any uh, problem that is involved with mixing something or mixing one or two components to form another product. So the range of a mixture design, unlike a process design, is always ranging from 0 to 1. While a process design ranges from -1 to 1, a mixture design ranges from 0 to 1. So the lower limit, the lower limit of component X is always 0, and the upper limit of component X is always 1, because in a mixture design, the sum of component proportion is always equal to 1 or to 100. So with that said, let's consider this student who wants to formulate a diet from 3 raw materials, and the student has predetermined the ranges of or the limit of substitution of those raw ingredients. The ingredients: wheat flour, soybean flour, and fruit powder are these ranges. So if we consider this equation to convert real values to coded or to pseudo values, you will see that we need to evaluate for L of I. We need to evaluate for L, and L of I here is simply the lower limit of component X of I. If X of I is equal to wheat flour, then L of I be equals to 50, 10 for soybeans, and 5 for fruit powder. So L, which is equals to the sum of all the lower limits, these are the lower limits. L, which is the sum of all the lower limits, will be equals to 65, and 100 minus L will be equals to 35. So if you substitute these values in this equation, either of the two equations, then we are going to have this final equation. So with this final equation, you can convert any pseudo value to real value, or any real value to pseudo value. For example, if we have a value 50 here, we can convert this 50 to a pseudo component by simply substituting 50 here. 50 minus 50 will be 0 divided by 35, which equals to 0. But this will boil down to this limit here, where I said the lower limit of a mixture component is always 0, and the upper limit is always equal 1. So if I substitute 85 here, I will have 85 minus 50, which is equals to 35 divided by 35, which equals to 1. And it will also boil down to this limit here, where I said the upper limit of a mixture component is always equals to 1. So what basically I mean is that anywhere you see 0 in a mixture experimental setup, know that they are referring to the lower limit of that component. Anywhere you see 1, know that they are referring to the upper limit of that component. So if we do the same for wheat flour and fruit powder, we are going to have these equations. And with these equations, you can convert any value within this range from 50 to 85, from 10 to 45, and from 5 to 40. So here you have the core concept of experimental design explained. I hope you enjoyed the breakdown. And if you did, you just hit a like. If you're not yet subscribed, you can subscribe so that you won't miss out on any content. And again, in your own opinion, what do you think is the best component or is the core component according to the project you're working on? Which of these components best describes what you're working on or is best fitting what you're working on? You can post your answer on the comment section. So thanks for watching. I will see you in the next video.